Today we're going to talk about the product rule and the quotient rule for differentiation. So we'll start with the product rule. The product rule says that if f of x and g of x are both differentiable functions, then the derivative of f of x times g of x will be the derivative of f of x times g of x plus f of x times the derivative of g of x. Now, because multiplication is commutative and that 2 times 3 is the same thing as 3 times 2, we may end up switching this order here and saying that the derivative of f of x times g of x is the derivative of f times g plus the derivative of g times f. Now, sometimes we'll denote this that if we had u times v and we were taking u times v's derivative, it would be u prime v plus u v prime. Or again, we can switch that u and v prime there. So that's a little shorthand if you want to use that. So let's take a look at an example. Let's find the derivative of x squared times x plus 2. Well, first of all, how do we know we need to use product rule? Product rule is any time you have variable times variable. So when you read the function out loud, if you say the name of the variable, then you say the name times, and then you say the name of the variable again, variable times variable tells you you need to use the product rule. So here we have x squared times x plus 2, variable times variable. Let's use the product rule. Now, the product rule was big and long, and it looks kind of messy, so how do we know that it works? I know what your instinct is telling you. Your instinct is saying, well, if I was going to take the derivative of x squared times x plus 2, I would just take the derivative of x squared times the derivative of x plus 2. The derivative of x squared is 2x, and the derivative of x plus 2 is 1, and so that would give us a derivative of 2x. But if we use the rule, which says we need to take the derivative of x squared times x plus 2 plus x squared times the derivative of x plus 2, we would get 2x times x plus 2 plus x squared times 1. Now, when we simplify that, let's go ahead and distribute that 2x and combine like terms, we would get a derivative of 3x squared plus 4x. Now, our instinct gave us 2x, the rule gave us 3x squared plus 4x, and as you can see, those are two completely different answers. So which one is right? Let's revisit the original function, x squared times x plus 2. What if instead of using the product rule, we distributed that x squared and we got x cubed plus 2x squared? Now we would be able to find the derivative using our 4 basic derivative rules, right? Well, remember our instinct told us 2x, but our rule gave us 3x squared plus 4x. Which one is right? The rule. Now, I know what you're asking. You're saying, well, why wouldn't I just distribute to begin with and use the 4 basic derivative rules rather than trying to use and know this product rule? And that's a great question. The thing is, sometimes it won't be as easy to distribute. It would make the problem a lot longer and harder and a lot more room for error. And also, you'll see later in the semester and next semester that there will be situations where you can't actually get away from the product rule. There's no way to distribute and combine like terms and avoid the product rule. So let's take a look at another example. We have 4x to the 5th plus 9x cubed minus 11x plus 7 times 5x cubed minus x squared plus 4x minus 5. Now this is a really big, long thing that if you really wanted to take every term in the first group and multiply it to every term in the second group, combine like terms, and then take the derivative, you're welcome to do so, but that's going to be very time consuming and it's going to leave you a lot of room for error. Instead, since we have variable times variable, let's use our product rule. Derivative of the first times the second plus the first times the derivative of the second. And when we do that, when we take the derivative of the first times the second plus the original first times the derivative of the second, we can actually just leave our answer like that. I'm not going to ask you to simplify that. If I had asked you to simplify that, then you'd have to distribute these two terms together, and combine all your like terms, and that would have been a lot easier just to distribute these two terms together and use your 4 basic derivative rules. So I would expect in a situation like this that you'd leave your answer like that. Let's look at another example. Let's take the derivative of s of t, which is the square root of t times the cube root of t to the 5th minus t. Now remember, we don't have a derivative rule for radicals. So we don't know how to take the derivative of the square root or the cube root or anything like that. So we will have to rewrite this in terms of fraction or rational exponent. So instead of the square root of t, that would be t to the 1/2. And instead of the cube root of t to the 5th, that would be t to the 5/3. And so now we have variable times variable. Let's use our product rule. Derivative of the first times the second plus the first times the derivative of the second. And we can actually leave our answer just like that. But if you want, you can get rid of the negative exponent and put the answer back into radical form. And if you do that, great. If you don't, that's okay. We've discussed before how sometimes it's necessary to get rid of negative exponents and put it back in radical form. So you need to know that these two answers are the same. Let's do another example using the product rule. What if I wanted you to find the equation of the tangent line of the function x squared plus 1 times 3x squared minus 4 at x equals 2? Now remember, to write the equation of any line, you need a slope and a point. Here we don't have a slope and we don't have an actual point. We have part of a point. So the first thing we should do is find the point. So I want to know what is the y value or the function value when x is equal to negative 2. So y, the second part of that ordered pair, will be the function evaluated at negative 2. And when I find that, I get 40. So I'm finding the equation of the tangent line at the ordered pair, negative 2, 40. So now we have our point. The next thing we need is our slope. Remember, the slope of a tangent line is found by the derivative. So looking back on this function here, you will see it's variable times variable. So when I go to find the derivative, I will go ahead and use the product rule. Derivative of the first times the second plus the derivative of the second times the first. So here I have my product rule. I found my derivative, and now my slope will be the derivative evaluated at negative 2. Remember, the derivative just gives you the formula to find the slope of the tangent line at any point. We specifically want it when x equals negative 2 at the ordered pair negative 2, 40. So the slope we're looking for will be the derivative evaluated at negative 2. So when I plug negative 2 into my derivative, I will get a slope of negative 92. So now I have a slope of negative 92, a point of negative 2, 40. I'm ready to find my y equals mx plus b. I'll plug in m, x, and y, and I'll solve for b, and I get b equals negative 144. So now I have my m and my b. I can substitute those into my y equals mx plus b to realize that my tangent line is negative y equals negative 92x minus 144. So there's the product rule. Now let's talk about the quotient rule. The quotient rule says if f of x and g of x are both differentiable functions, then the derivative of f of x over g of x would be the derivative of f of x times g of x minus f of x times the derivative of g of x all over g of x squared. Now again, because multiplication is commutative, sometimes we switched f of x and g prime of x, and we would say that the derivative of f of x over g of x is the derivative of f of x times g of x minus the derivative of g of x times f of x all over g of x squared. There is a short way to say it. If you have u over v and you're taking the derivative of u over v, it's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So let's take a look at some examples of the quotient rule. If we were going to start with x to the fifth over x cubed, variable over variable tells you you're going to have to use the quotient rule. Well, I know what your instinct is saying. Just like with the product rule, with the quotient rule, you're saying, why wouldn't you just do the derivative of the top over the derivative of the bottom, which would give us 5x to the fourth over 3x squared. Now remember, like bases being divided, you subtract their exponent, so that would reduce to 5/3 x squared. Now if we actually apply the rule and we take the derivative of the top times the bottom, minus the top times the derivative of the bottom all over the bottom squared, we would get this right here, derivative of the top, 5x to the fourth, times the bottom, x cubed, minus the derivative of the bottom, 3x squared, times the top, x to the fifth, all over the bottom, x cubed squared. Now, let's simplify this. 5x to the fourth times x to the third will be 5x to the seventh. 3x squared times x to the fifth would be 3x to the seventh. And x cubed squared would be x to the sixth. These are like terms. We can go ahead and subtract those. And we get 2x to the seventh over x to the sixth. And again, like bases being divided, we can subtract their exponents, and that would give us 2x to the 1, or just 2x. So our instinct told us that the derivative was 5/3 x squared, But the rule tells us that the derivative is 2x. Which one is right? Let's revisit that original function again. As we said, like bases being divided, you can subtract their exponents, so x to the 5th over x cubed is really just x squared. Well, what's the derivative of x squared? Is it what our instinct told us, or is it what the rule gave us? The rule actually works. Now I know what you're saying. Why wouldn't we just apply or simplify that quotient to begin with and use our 4 basic derivative rules? Well, look at this first example. That's not going to work. There's no way to simplify 4x cubed minus 5x squared over x to the 9th to be able to use your 4 basic derivative rules. If you have variable over variable, you have to use the quotient rule. So we'll set this up. We'll take the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. Now let's go ahead and simplify this where we'll distribute this out. This is what you refer to as FOIL, first, outside, inside, last. And we'll go ahead and distribute this -1 here. For the bottom, x minus 9 squared isn't going to get any more simplified than that, so we can just leave that. And when we combine our terms on the top, we get 8x cubed minus 113x squared plus 90x all over x minus 9 squared. And that's a perfectly acceptable answer. I would expect that you would leave it like that. Let's do another example. Let's take the derivative of 3x minus 1 all over the square root of x. Again, we have variable over variable, so we're going to need to use the quotient rule here. So we'll take the So anytime you have a radical, we need to rewrite that as a fraction exponent. So we'll rewrite the square root of x as x to the 1/2. And now we'll take the derivative of the top, which is 3, times the bottom, x to the 1/2, minus the top, which is 3x minus 1, times the derivative of the bottom, 1/2 x to the -1/2, all over the bottom squared. And so now let's simplify this a little bit, where if we get rid of the negative exponent and put it back into radical form, we have 1 over 2 times the square root of x. Putting this back in radical form, we have the square root of x. Putting this back in the radical form, we have the square root of x squared. So, of course, we can multiply these together, and we get 3x minus 1 over 2 times the square root of x. The square root of x squared is x, and here's our nice simplified answer. And I would expect that you would leave your answer just like that. So let's see an application problem of this. Suppose the revenue from the sale of x units of a product is given by R of x equals x squared plus 50x over 2x plus 2 plus 10x minus 1,000. How fast is the revenue changing when 49 units are sold? Now, to measure how fast something is changing at a given instant, that's your instantaneous rate of change. What measures the instantaneous rate of change? A derivative. At what instant? At 49 units. In other words, we are looking for the derivative of the revenue at x equals 49. Now, notice here, we can take the derivative of this first piece using the the quotient rule. We can take the derivative of this and this, so this is also an application of the sum and difference rule. If you can take the derivative of each of the pieces, you can take the derivative of the whole. It just turns out that this first piece we will have to use the quotient rule. So we'll do the derivative of the top times the bottom, plus the derivative of the bottom times the top, all over the bottom squared, plus the derivative of 10x is 10, and the derivative of 1,000 is 0. Let's go ahead and now plug in 49, because I want to know what is the rate that this function is changing at 49 units. So when I go ahead and I plug in 49, replacing each and every one of these x's with 49, I can start to simplify. 2 times 49 is 98 plus 50, times 2 times 98, or 2 times 49 is 98 plus 2, minus 2 times 49 squared is 2401, plus 50 times 49 is 2450, all over 2 times 49 plus 2 squared, and then we have this plus 10 here. When I actually start to simplify this out and I do my math here, I end up getting that r prime at 49 is 10.5098. Now, word problems are asked in words. They should be answered in words. So at what rate is the revenue changing? The revenue is increasing by about $10.51